Hi folks, this is Mr. Defy, and in this video I will be showing you how to graph exponential functions by making a table first. In this first example, you can see that our base is a fraction 1/3 and our exponent is right up there, the variable x. One of the easiest ways to make the graph of an exponential function is by making a table. In my table here, I like to add a couple of extra columns to include space for the function and the ordered pair. So without saying much more, let's go ahead and jump right in. So my inputs are everything on the left side, you see here. Starting with small numbers, I think is recommended because with exponents, things can get big pretty fast, or they can get really tiny very fast as well, as you'll see in a little bit. So if our input is 0, all you have to do is plug that in to our function, and what you get is 1/3 to the power of 0. As you may remember, anything to the power of 0 is just a 1, so our output is a 1. Our output goes here, which then creates an ordered pair of input, comma, output. Okay, that's my first point. My second one works the same way. So if I just keep going, this is 1/3 to the power of 1. Well, that's just 1/3. So I have an output of the same, and my ordered pair is 1, comma, 1/3. Okay, continuing on, if I have a -1 as my input, this gives me an exponent of -1. Now, if you remember, when you have negative exponents, you have to do the reciprocal. So this actually becomes 3/1, which is then just 3. So that's my output, and I have -1, comma 3. If I have an input of 2, I get 1/3 to the power of 2. Now this would actually be 1/3 times 1/3. So 1/3 times another 1/3 is 1/9. And that's what I was talking about earlier when I said that your outputs can become very small with just a slightly big number, like a 2, for example. So our output is 1/9. So it's 2, comma 1/9. -2 gives 1/3 to the power of -2, and just like with the -1, a negative power means do the reciprocal. So this is actually 3 to the power of +2, which is just +9. So that's my output, and I have -2, comma +9. We could go on and get more values here, but sometimes having about 4 to 5, I recommend 5 as a minimum, is optimal. So let's go ahead and see where this gets us so far. So if I transfer my ordered pairs onto this coordinate plane, then what I get is the following. 0, 1, I'll use pink. 0, 1 is over here. That's easy. That's 0, 1. We'll do that once again. So here's 0, 1. 1 and 1/3. So 1, comma 1/3. Well, here's 1 and 1/3. Now 1/3 is really small, but if you think of it, you can kind of estimate where this is. 1/2 would be about right there, right? One half is about right there. 1/3 would be a little less than that. So 1/3, roughly about right here. Okay, it doesn't have to be precise. That could be about 1/3 or 0.333. Okay, so that's my other point. -1 and +3. -1, +3, that's easy. That's just regular integers like that. But you can begin to see that these 3 points are not linear. They actually do form the beginnings of a curve. And we'll see the curve a lot more clearly once we plot the other points. So let's go on. 2, comma 1/9. Now 1/9 is very, very small. On a coordinate plane scale, a little difficult to plot that point. So what you want to do is maybe estimate, or else choose a different input number that doesn't give you something like 1/9. But let's go ahead and do that. So 2, comma 1/9. Now 1/3 already put me almost right on that x-axis. But remember, no matter how close you get to the x-axis, you'll never actually touch it. Okay, so never put a point directly on top of the x-axis. That would be wrong. All right, next one would be, the last one is actually -2 and +9. So -2, +9, -2, +9, that's right over here. That's pretty far away, but it's enough for us to see how this thing is going to become. So this is clearly a curve, and it dips sharply, and it gets real close to the x-axis, but it never actually touches it. Now I'm going to do my best to connect all these points in a curving manner, and if I mess up, forgive me, but I'll do my best not to. So here I go. It'll be something like this. Okay, now as you can see, it gets real close to that x-axis. Like I said, you'll never actually touch it. So if I were to zoom in, I can continue and get even closer. Now I'll put an arrow and stop right there. I'll put an arrow here and stop right there as well. This would be the graph of your exponential function. And because it is decreasing as you go from left to right, this thing is going down. Because it's decreasing, this is called exponential decay. Okay, so exponential decay. Decay means the decline of something. And there you have it. Okay. One thing that I would recommend, again, just to get this into your head, when you're choosing input numbers, go small. 0 is your friend, so don't be afraid to use that number. And then just do inverses like 1, -1, 2, -2. If you see that your output number, like in this fourth row here, if you see that your output number is something incredibly small, like 1/9, you could always go back and rethink your input number and see if you can get something a little friendlier to work with. But again, these fractions are to be estimated, but you have to do a good estimate so that your points, when connected, do form a nice smooth curve. So that's example 1. Going on to example 2. So example 2 is a little different because here we have a coefficient in front of our base and power. In the first example, we didn't have anything like that. We had just a base and power by itself. 1/3 to the power of x, that's it. But over here, you can see that we have a 1/2 as our multiplier. So we have to take that into consideration when we are doing our work here, okay? So we're going to be taking half of whatever outcome is from there, okay? Just keep that in mind. It's half of whatever you get after doing this 5 to the power of your x. All right, so let's see what the outcome becomes. So here are my input numbers once again, and I'll go ahead and begin. Oh, actually, this is incorrect. I need to change this over here. I'm going to do that quick adjustment. Sorry about that. This is 1/2 times 5 to the x. All right, and with that, let's begin. If my x is 0, life is already easier because 1/2 times 5 to the 0 power is like saying 1/2 times 1. Anything to the 0 power becomes a 1. So that just goes away, becomes a 1. You get 1/2, okay? But you can see already our first output, just by using a 0, our first output is already just a 1/2. Okay, moving on. So we have 0, 1/2. Let's see if things change up for us. If our x is a 1, then I have 1/2 times 5 to the first power, which is like saying 1/2 times 5, which is 5/2. So my output is 5/2. So 1, 5/2. If you're wondering how in the world would I graph or plot a point when it's 1, 5/2, I'll explain that later. Moving on, if your input is -1, it would be 1/2 times 5 to the -1 power. Remember that negative powers mean you do the reciprocal, so this is actually 1/2 times 1/5. Okay, and that would be 1/10. So 1/10, and you get -1, 1/10. Okay, again, a very small fraction, which means that we're going to be very, very, very close to that x-axis. Let's see where that gets us. When you have a 2, what you get is 1/2 times 5 to the second power. Well, that's like saying 1/2 times 25, which is 25 over 2. So 25 over 2. 2 comma 25 over 2. Negative 2, you have 1/2 times 5 to the negative second power. That's like saying 1/2 times, do the reciprocal of that, that's like saying 1/2 times 1 over 25. Oh man, this will be a very small fraction indeed. So this will be 1 over 50. And to be honest, I think I'm going to scrap this one because trying to plot negative 2 comma 1 over 50, that's going to be very challenging for me in this space that I have here. So I might just go ahead and leave that last row out of my graph and just do the rest. But let's see. All right, so let's see what we get so far. So I have 0 comma 1/2. So 0 comma 1/2 would be here. 0 comma 1/2. Okay, this is 1. So half of that, that's 0 comma 1/2. The next one is 1 comma 5 over 2. Now, 5 over 2 could be made into a decimal. That would make it easier to pinpoint exactly where this thing belongs. So I could transform this into 1 comma 2.5. If you divide 5 by 2, you get 2.5, and that means the same thing as 5 over 2. And that makes it very clear. 1 comma 2.5 means go out 1, go up 2, this is 3, right? So 2.5 would be right here, okay, right there. So 1 comma 2.5. Okay, next one is negative 1 comma 1 over 10. So negative 1 comma 1 over 10. Negative 1 is here. 1 over 10 will be very close to the x-axis. Again, estimating, but never right on it. Like that. I can already see that this is increasing, not decreasing, okay, as you go left to right. 2 and 25 over 2. I'm going to transform that into 2 comma. If you divide 25 by 2, what you get is 12.5. Okay, and I'm going to go ahead and leave this out. So I'm leaving out the last row. I decided we're not going to do this one. Okay, this is too small. So we're going to stop at 12.5, 2 comma 12.5. So 2 comma 12 all the way up here, and then 0.5. If this is 13, 12.5 would be right there. This is 2 comma 12.5. And so the graph is definitely going to be increasing this time. And although these 2 points, this one here and this one here, are very far away from each other, I do have enough to go ahead and try to create a clear graph. So I'm going to do my best again. Forgive me if I mess up, but here I go. Again, you want to approach this as a curve like this, okay? And if I zoom in a little more, you can see this gets super close. And in fact, it looks like I'm touching the x-axis, but really what's happening is that I'm barely grazing it. I'm not even grazing it. I'm just hovering above it all the time. No matter how close it seems to get, it never lands on that x-axis, okay? And there you go. So this graph is increasing at a very steep rate, and because of that, this is called an exponential growth. Exponential growth, okay? Which is the opposite of an exponential decay. And you can see that the graphs indeed look different from each other. This is going up as you go left to right. This is going down as you go left to right. So I hope these 2 examples helped you out. Making tables requires patience because you're dealing with exponents here, and you have to be careful not to muddle up the laws of exponents when you're dealing with those negative inputs. Be careful with that. Anyway, thanks for watching. Stop by, leave a comment, and I'll see you next time. Bye-bye.